Hello! Welcome to my second presentation, Mini Presentation B, for Math 420, History and Philosophy of Mathematics, for the fall 2019 semester at Mayville State University. My name is Jonathan Seagrave, and my presentation is on the golden ratio. I hope you enjoy it. In 1509, Italian mathematician Lucia Pacioli, a close friend of Leonardo da Vinci, published Divina Proportione, a treatise on the number that is now widely known as the golden ratio. But what is this golden ratio? Well, I wasn't able to get my hands on an English translation of Pacioli's Divine Proportion, and I'm not fluent in Italian. You may be able to tell by my poor pronunciation of both Pacioli's name and the title of his book. I was, however, able to get an English translation of Euclid's Elements, written some 1800 years before Pacioli's text. In Book 6, Euclid writes about the golden ratio, which he calls the mean proportion, and he explains how to construct it. Take any line, he says. We're going to call this line AB, and from one end extend a second line exactly 1/2 the length of AB perpendicularly to create a right triangle. Let's call the third vertex of our triangle point C. Now we have a triangle ABC, where AB is twice the length of BC. Divide the hypotenuse AC of this triangle into two sections, AD and DC, where DC is the same length as BC. It turns out now that the ratio of AB to AD is the mean proportion. QED, Euclid writes. Thus it is shown. Well, other than demonstrating how to construct it, Euclid doesn't say anything about the golden ratio, which is probably why Pickover chose to pin down the golden ratio to the year 1509 when Pacioli published his work. But what is the golden ratio? Didn't we just ask that? The numerical value is irrational, something that really got under the skin of the Pythagoreans, if we're to believe the legends. In 2002, Mario Livio wrote The Golden Ratio, the Story of Phi, the World's Most Astonishing Number. And in it, he writes that in the 5th century BCE, when the Greek mathematician Hippasus of Metapontum discovered that the golden ratio is neither a whole number nor even a ratio of two whole numbers, it absolutely shocked the other followers of Pythagoras. The Pythagorean worldview was based on an extreme admiration for the intrinsic properties of whole numbers and their ratios, and their presumed role in the cosmos. The realization that there exist numbers, like the golden ratio, that go on forever without displaying any repetition or pattern caused a true philosophical crisis. Legend even claims that, overwhelmed by this stupendous discovery, the Pythagoreans sacrificed 100 oxen in awe, although this appears highly unlikely, given the fact that the Pythagoreans were strict vegetarians. So, we know it's irrational, and we know that the Greeks knew about it. What else is there to know? Well, let's back up a bit and review. If we divide a line into two segments, where the ratio of the whole line to the long segment is the same as the ratio of the long segment to the short segment, then the ratio we have is the golden ratio. Today, it's commonly symbolized by the Greek letter phi. A golden rectangle is a rectangle where the ratio of its long edge to its short edge is the golden ratio. In such a rectangle, it's possible to divide it into a square and a smaller rectangle, and by doing so, you will have created a second, smaller golden rectangle. You can continue this process, producing smaller and smaller golden rectangles indefinitely. The point to which all these golden rectangles converge, writes Pickover, is sometimes called the eye of God. Indeed, the golden rectangle is the only rectangle from which a square can be cut, so that the remaining rectangle will always be of similar proportion to the original. But what is its value? How is it that we've been talking about a number for 4.5 minutes and we still haven't said what its value is? Well, recall our two line segments, A and B. We know that the ratio of A to B is the same as the ratio of A plus B to A. And we've said that this is phi. So if we expand the A plus B over A into A over A plus B over A, we see that it's equivalent to 1 plus B over A or 1 plus 1 over phi. So phi is equal to its own reciprocal plus 1. That's kind of cool. There's a couple of different ways that we can get a value out of this. I'm going to explore the less interesting one first. Multiplying both sides by phi, we find that phi squared is equal to phi plus 1. We can move everything over to one side and use the quadratic formula to solve for the roots of this polynomial. We find that we have two roots at 1 plus and minus the square root of 5 all over 2. Well, remember that we're solving for a ratio that you can see from our picture that is a bit more than a half. It's clearly not negative, so we choose the positive root for our value of phi. The result is that phi is equal to 1 plus the square root of 5 all over 2. I think a more interesting solution is to recall that phi is equal to 1 plus its own reciprocal. That means that it's equal to 1 plus 1 over 1 plus its reciprocal. But wait, that means it's equal to 1 plus 1 over 1 plus 1 over 1 plus 1 over itself, not its reciprocal. It gets confusing. Indeed, it does go on forever. And this type of construction is called a continued fraction. It turns out that any real number can be written as a continued fraction, and often they're easy to figure out. Say, for example, that you want to find the continued fraction of pi. Here's how we do it. Wait, I'm back from the future, and you don't want to go there. After another 7 minutes of explaining continued fractions, I've realized that you're just going to have to look this one up on your own. Numberphile and Mathologer both have excellent videos to explore if you want to see more. I really wanted to get to the point where I could explain why some consider phi to be the most irrational number of all. It has to do with how quickly the continued fractions converge, but you're going to have to learn about it on your own. I couldn't explain this in a reasonable amount of time. Sorry. Anyway, back to phi. Leonardo of Pisa, known to us as Fibonacci, left us a sequence of numbers that we now call the Fibonacci sequence. Fibonacci himself, says Mario Livio, came up with the numbers as a solution to a problem involving the growth rate of a population of rabbits. The sequence starts with two ones. Any consecutive term is just the sum of the two previous terms. So the third term is 2, and the fourth is 3, then 5, and 8, and 13, and so on. What Fibonacci was unaware of, again according to Livio, was that his number sequence progressed farther and farther. The ratio of the individual terms converged to something that was proven to be irrational by the Greeks. Yes, indeed, the ratio of consecutive terms of the Fibonacci sequence gets closer and closer to phi as the sequence progresses. Phi shows up in nature. Phi shows up in art. Phi shows up in music. If you ever get approached in a dark alley by mystical Illuminati-type weirdo mathematical people and they ask you for a secret number, the answer might be phi. It's probably 42, but it might be phi. For more, have a look at some Numberphile videos. I've left some links here. Or the Mathologer videos are also very good. All of these should be clickable URLs in this presentation's description. Enjoy!